If I have a multiple lens or mirror system, you work it exactly the same way. You just do one step at a time, okay? So I drew one out. Whoops. I drew one out. We're not going to look at the math on one just yet, but I want to show you what the ray trace of a multiple lens would look like. Oh, and it's going to be crooked. Let me see if I can change the orientation of this. Probably not. Okay, well, maybe y'all can tell what's going on. You can look at it on your example. So I'll go ahead and show it and show you, and then you can look at it on your examples. So, all right. So y'all just have to kind of bear with me on this because I didn't think about how to turn this sideways. Okay, so what I do is there's two lenses here, okay? There's two convex lenses and here's my object. So I'm going to ray trace the first one and I'm going to completely ignore the second one. I'm going to act like it's not even there. So in parallel, out through the focal point, in through the focal point, out parallel, and there's my little image, okay? And I know I'm outside the radius of curvature. It's going to be reduced. It's going to be real. Now, here's the thing though. The image formed by the first thing becomes the object for the second thing. So now I'm going to forget that lens number one is there and that original object's there, and I'm only going to ray trace using this as my object. So in parallel, out through the focal point, and then in through the focal point, which is here, out parallel, and they come together right there, so it forms a upright, enlarged image. Now, here's the thing. You do it one step at a time. If I had a third one, then this would become the object for my third lens. So in a multi-lens mirror system, you do it one step at a time. You do the math one step at a time. You work everything out for the first lens or mirror, and then you go to the second one, okay? So the final image here is a combination of these two. So what it'll ask you usually is, what is the final image compared to the original object? So in this case, it's a real image, but it's upright because it's the same as my object. Now, for the magnification, I have to multiply the magnification I got from lens one by the magnification I got for lens two. All right, so I would find magnification using the equation for lens number one, and I would find the magnification using the equation for lens number two and multiply them together. Okay, that shows up in an example problem if you do a problem where you have multiple lenses and mirrors. So this is an example of that. This is chapter 19, and I forgot to write the problem number on there, but I will tell you what it is. It is chapter 19, problem, where'd it go? Oh, problem 60, okay? Chapter 19, problem 60, and it says a lens with a focal length of 25 centimeters is placed 40 centimeters in front of a lens with a focal length of 5 centimeters. How far from the second lens is the final image formed of an object infinitely far from the first lens? Is the image far behind the second lens? Okay, so I'm going to ignore the second lens to start with. I'm going to do the math for the first lens. So I'm going to use the thin lens equation for number one. So they told me an object infinitely far away. So this is like we're looking at something really distant, or maybe we're looking at a star or something like that. So its object distance is essentially infinite. Now remember, the definition of the focal point is where light from an infinitely far object would focus. So I can do the math, or I can just remember that. So 1/25, which is the focal length of the first lens, is equal to 1/infinity plus 1/s prime. Well, what's 1/infinity? It's 0. So s prime is 25. That's the definition of the focal point. But now, that becomes the object for the second lens. So now I'm going to ignore lens 1. I'm going to only look at lens number 2. So now I need to find the distance the image is from the first lens, or from the second lens, excuse me. I need to find out where S1 formed relative to the second lens. So they're 40 centimeters apart. S prime for the first lens was 25. So this distance right here is 40 minus 25. Okay, so that'd be 15. So now I'm going to go to lens number 2. So the image of number 1 becomes the object for number 2. So 40 minus S prime of 1, which is 40 minus 25, is 15. So now I'm going to use the thin lens for number 2. I'm going to ignore 1. So 1 over the focal length, which they gave me was 5, is equal to 1 over the object distance for 2, which is this 15 that I just found, plus 1 over S prime for 2. Got me a common denominator again, did my math. S2 prime is 7.5 centimeters, which is a positive number, which tells me that's a real image. And it says since S2 prime is positive, it is to the right or in front of the second lens. So you're doing 2 problems. You're just doing problem number 1 for the first lens, then finding the new distance, problem number 2. Okay? All right.